All right, so oh, she's here. We're going to look at one last proposition before we start real numbers, real number analysis. The proposition is about what is in each equivalence class. So write this down. So this should be after the definition of an equivalence class. We're now going to look at what is in each equivalence class. All right, so here we go. If R is an equivalence relation, good morning, if that's what you said. I didn't hear clearly what you said. Oh, okay. Were you asking something? Michaela?
Sir?
Were you asking something a while ago? Or are you just saying good morning?
What you said we're going to look at?
A little further information about equivalence classes. Just one look at theorem.
Okay, sir.
Yeah. I missed it out last time. So here's what it says. If R is an equivalence relation, if R, capital R, is an equivalence relation on a set A, remember sets are capital, on a set A, then every A in A, so every element A in A, then every A in A is in exactly one equivalence class. Then every A in A is in exactly one equivalence class. Full stop. Therefore, if, all right, let's say that way, therefore, if A is related to B if and only if and only if the equivalence class of A is the equivalence class of B, or is equal to the equivalence class of B.
Morning, sir.
Morning. We started at 5 minutes past like you asked. So don't come cuss us this morning.
I can't tell you what happened to me. I have to keep that one here.
Oh, we're not too late still, just 2 minutes. Well, 7 really, but for your grace
So
period,
this is
2
the
minutes.
first thing that I'm looking at?
Yes.
Okay, sir.
All right, so that is out of the way. You're going to use that for some of the questions that we might encounter later. So if R is a equivalence relation on A, then every A in A is in exactly one equivalence class. So A is related to B if and only if the equivalence class of A is equal to the equivalence class of B. So an example of that the last example I gave you. I should do another one now. No, I want to get the real number. Maybe when I get to the end of real numbers for today, then I can just do an example of everything. I want to get definitions now. There are quite a few for real numbers. So we're going to look at real numbers now. The first thing we're going to look at is the basic properties of real numbers. Real numbers. Remember the course is real number analysis. So we finally gotten to that stage now. So we've gone through the basics. Time to look at real numbers. Definition number 1 for real numbers. It is an ordered set. So here's what it says. The definition of an ordered set. So right now we're looking at the basic properties of numbers if you want to get a subtopic really. So first definition, ordered set. An ordered set, ordered, so it's ordered, O-R-D-E-R-E-D. An ordered set is a set S, capital S, together, so set, right, on the board is a set S, together with a relation less than, that's the relation. An ordered set is a set S, comma, together with a relation less than. So you should actually write the word relation, and then after that you have less than. Such that A, part A, for any x, y, x or y in S, such that for any x or y in S, exactly one of, for any x or y in S, exactly one of x less than y, x equals y, or y less than x holds. Exactly one of x less than y, x equal y, or y less than x holds. So for the two numbers, one of those properties must work for those two numbers. You did one number is less than the other, one is equal to the other, or the other one, the previous, or one of them is the next one. If it's A and B or X and Y, either X is less than Y or Y is less than X, or they're equal. We know that to be true. B, so that was A. B, if X, need some space up here. If X less than Y and Y is less than Z, so part B, if X is less than Y and Y is less than Z, then what? Should be able to figure this out. Come on, smart people. If X is less than Y and Y is less than Z, then what do you think happens?
X is less than Z.
There you go. Remember which property that is? Oh, not property, sorry. Which relation? Relation.
Transitive.
Transitive, right? Oh, you guys know what I'm talking about. Because remember, we said that less than is transitive. Yeah, that's it. That's the first definition. So that's an ordered set has to follow that setup. For it to be an ordered set, you should be able to put the numbers in order. One less than the other, or they're equal. Next definition. So that one is straightforward. I don't think you have any questions about that. Next definition. So we're still continuing the ordered set business, but we're going a little more detailed. Let the set E be a subset of set S. So let set E be a subset of set S. Where S is an ordered set. So let set E be a subset of set S, comma, where S is an ordered set. Full stop. So we have 4 things to look at now. Part A. If there exists a B in S, if there exists an element B in S, if there exists a B in S, such that x is less than or equal to b for all x in E. It sounds like it's going to run about, but you have to be careful. Let me say it again. If there exists an element B, you don't hear the word element, but make you know it's an element. If there exists an element B in S such that x is less than or equal to B for all x in E, then we say E, set E, is bounded above. Is bounded above. And B, question coming in now. Yes, Jermaine?
So repeat the last part after it says X in E.
Then we say E is bounded above. Then we say
Okay,
E is bounded above. And, no finish it. Bounded above. And B is an upper bound of E. And B is an upper bound of E.
sir. B is the upper bound of itself?
Of E. They said E.
Of
Remember E?
E, okay.
Yeah.
B is the upper bound of E, okay.
There we go. Next. If there exists, oh, sorry, B. That was A a while ago, part A. Part B. You're going to have right down to part D. A, B, C, D. So now we're going to B. This is now talking about bounded below. If there exists a B in S, such that, start just like the one a while ago. If there exists a B in S, such that and since it's bounded below, this time we're going to say such that x is greater than or equal to b. X is greater than or equal to b for all x in E. Yeah. Then we say E is bounded below. Then we say E is bounded below. Bounded right below. And B is a lower bound of E. Then we say E is bounded below and B is a lower bound of E. Or maybe I should say it this way. And element B is a lower bound of set E. We know what I'm talking about. Common letter is element, capital letter is set.
Sir, if there exists a element B in S such that X is greater than or equal to B, where X in E, then we say E is bounded
Below.
That's where you stopped?
No, sir. And B is a lower bound of E.
And
B, as in boy, is a lower bound of E. Egg.
okay, sir.
Got
Thank you.
that? Okay. Part C. So you have seen what is bounded below and what's bounded above. So I'm going back to that soon because I want to make sure. No matter of fact, let me deal with it right now before the next part confuses you. You notice that B did not necessarily come from E. Even though the E are, look here. First of all, we establish that E is a subset of S. Let me give you an example. Let's look at the integer. No, don't use integers. Use let's say we're talking about real numbers is the set S, and let's say the subset that we're looking at E, the subset E is this. We can just work easy. 5 to 10. Numbers from 5 to 10. A matter of fact. Yeah, I use 5 to 10, sure. I was going to use open brackets, but let's use the closed brackets. So this is our subset, E. It's a subset of R. Now, look at the first definition. The bounded above definition. If there exists a B in S, now remember S is the real numbers, you know. So I'm going to use the number 11. 11 is my B. So B is the 11. If there exists a B in S, such that all the x's in E are less than or equal to that B, as you can see, every number from 5 to 10 is less than or equal to 11. We can agree on that. All of the elements in, remember, x is all the elements in here. X is in the 5 to 10. If there exists a B, which is 11, such that every number in that set 5 to 10 is less than or equal to 11, then we say that the set 5 to 10 is bounded above, because all elements in that set was less than the 11 that came from the real numbers. That's what part A is saying. If you can find a number in the original set, or the way call it, the universal set, that is greater than or equal to all the elements in the previous set, subset, what is wrong with my throat? Then the set is bounded above. Excuse me. All right, yeah, that's better. Good. So if there exists a B in S, which is the real numbers, that's my example. So remember, you know, my S is the real numbers, and I took a subset 5 to 10 from those real numbers. So those are real numbers too, you know. All the numbers from 5 to 10. 5.5, 5.1, 8, 7, whatever. So if I can find a number in the real number set that is greater than or equal to all the numbers in that subset, then that subset is bounded above. That's what it's saying. For part B now, if you can find a number that is less than or equal to all those numbers, we could have used 5 as well. We could have used 5, because 5 is less than or equal to all of these. But the reason I used 11 a while ago is because I wanted to realize that, look at what it said. If there exists a B in S, it didn't have to come from the subset, as long as it is from the universal set that we took the subset from. So as long as we can find a number that is greater than or equal to all the numbers in that subset, it's bounded above. If you can find a number that is less than or equal to all the numbers in that subset, it's bounded below. That's what they're saying in their fancy English. Okay. Everyone seems to understand. Let's move on to part 3. I wanted to make sure this was clear before we get to part 3, because I might get mixed up now. So listen carefully again to part 3. If there exists an upper bound, listen carefully now. This is part C. Oh, geez, I hope you weren't writing anything out again. Well, you have told me. Part C. If there exists an upper bound B naught, make sure you see that how that's written, B subscript 0. If there exists an upper bound B naught of E, you hear where the B naught come from? I mean, upper bound of, here, what's the upper bound of? There exists an upper bound B naught of set E. Listen carefully now. Such that whenever B is an upper bound, such that whenever B, come on B now, not B naught, you know. So read it one more time, let's make sure it's clear. If there exists an upper bound B naught of set E, such that whenever B is an upper bound, or is any upper bound for E, such that whenever B is any upper bound for E, such that whenever B is any upper bound for E, we have this. After E, you should have, we have B naught is less than or equal to B. Then B naught is called,
Go over that
yes,
again,
Jeremy?
please.
If
Go over
there
that again, please.
exists an upper bound B naught of set E, such that whenever B is any upper bound for E, we have B naught less than or equal to B. You have that?
We have B
The thing on the board here.
naught. Okay.
Comma?
Okay, sir. Got it.
All right, good. Comma after the B naught, after the B, sorry. Comma after the B. Then B naught is called the least upper bound. Then B naught is called the least upper bound, or the fancy word now, or the supremum. You see, the people who did modern algebra and did this already, they may get confused now, you know, because they mix up supremum and maximum, not the same thing. But anyway, I won't mention the maximum, so hopefully you don't get confused. So let me read everything one more time now. If there exists an upper bound B naught of E, remember the upper bounds don't have to be a part of the set. They come from the original set S. So anyway, let me continue. If there exists an upper bound B naught of E, such that whenever B is any upper bound for E, we have B naught less than or equal to B, then B naught is called the least upper bound, or the supremum of E. So this is the supremum of the subset. Full stop. It is denoted sup E, or let's call it B naught, if we define it as the supremum. So whenever you want to write supremum, you write sup. So if it's a supremum of subset A, you write supremum of A. Since we're talking about subset E, we use supremum E. All right. So let me be very clear. The supremum does not have, the supremum must come from the overall set. That's what is important. It does not have to come from, a matter of fact, at no point in time did it mention that it comes from the subset E. It can, but it doesn't have to, but it has to come from the set S. All right. That's important to remember when I'm showing an example. It's important to remember that. Part D. It's the same thing, just turn around. Now I'm going to talk about lower bound. So part E, D, part D. If there exists a lower bound B naught, a matter of fact, tell you what, this way you don't get any confusion. You see what you wrote for part C? Write the same thing for part D, just replace upper with lower, and replace less than or equal to with greater than or equal to. So let me say that again.
Sir, just read it to us, please.
It's going to take long, man. I can't bother, man. I can read your writing faster than my read. All right, let me read. Write fast enough. If there exists a lower bound B naught, if there exists a lower bound B naught, not for get better yet, no, she's still miserable, of E, such that Oh, geez. Such that whenever B is any upper bound, Lord of mercy, reading the wrong one. Such that whenever B is any lower bound, sorry. Such that whenever B is any lower bound for E, we have B naught greater than or equal to B. Then B naught is called the greatest lower bound. Then B naught is called the greatest lower bound, or the infimum. Infimum. Whoops. So, infimum of E. And this is written infimum of E is the B naught. Assuming that's what we call it. And finally, part E. It's not really a part, but it's a name. But the main things are from A to D. So part E, when a set E is bounded above and below, when a set E is bounded above and bounded below, we say that E is bounded. So when it's bounded above and bounded below, we say that E is bounded. So you can't say a set is bounded unless it's bounded above and below. If it's just bounded above, it's bounded above. If it's just bounded below, then it's bounded below. But if it's bounded above and below, we just say bounded. All right. So let me explain to you now exactly what an infimum is. Let's say we're looking at the real number set. Let me show you two examples. Let's say we have this subset right here, the subset 6, 14. But we have a closed bracket at 6 and a open bracket at 14. All right. We can say that the set is bounded above and bounded below. Why? Because I...
Sir.
friend saying something? Oh, Jeremy, yes.
Sir, is it that you're going to give us, I know you're going to give us an example, but it seems like you're giving us an example for bounded. For bounded, are you going to give us an example for each of them separately?
Yes, that's what I'm doing.
Oh, that's what you're doing now? Okay. Oh, good, great. Thank you, sir.
Yeah. So we know that the set is bounded below because we can find a number that is less than or equal to every number in that set. Remember, that's the bounded below, you know. By the way, let me just make sure this is clear. This is our subset E. It came from the general set S, which is real numbers. So remember that to find something that bounds it above or bounds it below, we must get it from the set S. It doesn't have to come from E. Although if it does come from E, it's still coming from S because E is from S. All right, so here we go. To find to prove that the set is bounded below, we can use the number 4 because 4 is less than or equal to every number in that subset there, every number in 6, 14. So it is bounded below. But someone could have used 5, and that would also be true. 5 is less than or equal to all of these. Someone could have gone further to use 5.5, which is still less than or equal to all of those. But you notice what is happening? Each time I'm increasing the number, it is becoming greater than all the previous lower bounds. But so what I'm going to do now is find the greatest lower bound that is less than or equal to all the numbers in that set. And that number would be 6. 6 is less than or equal to every single number in that subset. Remember what I said, less than or equal to. So 6 is the infimum of this set, of this subset. How do I know that? Because you cannot find a number. So because look at this. Because the 6 is all of these right here, by the way, let's make sure you see. All these right here are B's. These are all lower bounds for our subset. Every B right here is a lower bound for our subset, but the 6 is the B naught. Why is that so? Because the 6 is the greatest lower bound that you can find. What is wrong with this? Yes, 6 is greater than or equal to all of those possible lower bounds. You cannot find a lower bound that is bigger than the 6, put it that way. That 6 is the greatest lower bound that can be found. So it is the infimum of that subset. Does anyone understand that?
That's B
Yes,
naught
that's B
greater
naught.
than or less than B, right?
Right. I mean, right over here? Yes. Because that 6 is greater than or equal to all of those B's that we had, the 4, the 5, the 5.5, 5.9, anything. Any lower bound you want to find for that subset, the 6 is greater than or equal to all of them, including the 6 too. Yeah. Any questions? Everybody understand that? Okay, no questions. So everybody understands that. Let's look for, I'm going to do two things at once now. I'm going to mention bounds above and find the supremum as well. So a while ago I showed you what bounded below is like. You can just find a number that is less than all of those. And to find the lowest one now, to find the greatest lower bound is finding the infimum. So the 6 is the infimum for that subset. So I'm going to, is anyone writing this off the board? I'm going to clear it off to the infimum. Supremum. I don't think there's anything to write really, but is anyone writing? 5, 4, 3,
No, sir.
2, 1. Okay. Using the same subset, 6, 14. All right. Let's look at some upper bounds. We can look at 15. 15 is greater than all of the numbers in that subset. See, 15 is greater than every number in 6 to 14. Also 16. Also 17. Should I start with those, Anyway, doesn't matter. But we can go a bit lower to 14. 14 is greater than every number in that subset, but at the same time, it is less than or equal to every number that we mentioned before. So the 14, you can't find a number, well, let me not say that yet. That 14 is less than or equal to all of those numbers before, less than the 15, less than the 16, less than the 17. So far the 14 is our least upper bound, so far. Can you find a number that is less than 14, but at the same time, it is greater than or equal to all numbers in that subset? Someone might say 13.999999999. But if you say 13.9999999, I can just simply say 13.9999999 and one more 9. Obviously where I'm going, So if you want to put a million 9s on this, I can put a million and 1. So what do you think is the supremum of that subset?
Sir, 13.
I'm not hearing you. How much is it? Lafern? Was Lafern or Michaela? I heard her female voice.
Sir, I would say 13.
13?
Yeah.
All right, Lafern says 13. Is 13.5 in that set? Is number 13.5 in our subset?
Yes, sir.
So all affirm. Remember your supremum minimum must be greater than all the numbers in the subset or equal to them. So we
So
can't use
Oh,
13
sir,
because
It has to be
oh,
14.
sir, I forgot that 14 doesn't necessarily have to be in the set for it to be the supremum, right?
right, you're thinking about maximum. That's why I said
Oh,
modern algebra will
yeah,
confuse you.
yes, right.
Mm-hmm.
Because 14 isn't in that set.
Right, it's not in there.
So
But as
14, I
Jermaine and
change my
the 14th
answer.
answer. Correct. Well done. So the supremum is 14. Why? Because 14 is greater than, it doesn't have to be equal, but it's greater than or equal to every number in the subset. At the same time, you cannot find a number smaller than 14 that is greater than or equal to every number in the subset. You won't be able to do that. So 14 is our least upper bound. It's a supremum. These are tricky, So you see the same thing that applies to the closed bracket applies to the open bracket. If you deal with real numbers, that's a trick.
sir,
Yeah. Go ahead.
but why do we put the equal on it? Because it can't be equal to because it's not in the set. So
Because I wouldn't say it's equal, it's greater than or equal to it.
right. But why?
Why put equal?
Mm, and
Because
and
that's the
that cannot
definition.
be and that's not an option.
It means not an option. It is an
Because
option, it's just that it's not met.
wow,
Remember, it's greater than or equal. It was an option, but this set can't meet that option. Because that's the definition the set has to be used. It has to fulfill that criteria, so we have to put it there.
okay.
Yeah.
Is it because we can have 13.99 forever, so we just round it off to 14? No.
Look here, but I'm gonna get technical and confuse yourself, As long as it is greater than or equal to them, that is fine.
All right, sir.
All right. You know what? I'm gonna give you one right here. So here's our subset. Prime numbers. So I'm just writing down. Prime numbers less than 70. So prime numbers less than 70. Find the infimum and the supremum of that. I'll be right back. I'll give you that try because I need to catch my clothes before the rain comes down hard. Soon come. So prime numbers less than 70. Find the infimum and find the supremum. Soon be back. All right, I'm back. What are the answers we got? Hello? You guys hear me?
Yes, sir.
Okay. So prime numbers. I should have said prime, no, less than 70. All right. So what are the answers? What's the infimum?
Dos.
2.
2, correct. So the infimum is 2. Let's call it set E. Since the infimum of E is 2, what's the supremum?
7 is
See it what?
What? 67.
Yeah, 16,
67.
67. Oh, I didn't
67.
hear the. What you call 7?
Huh?
What is it?
Huh?
I know see it
What?
60, but what did you say after 60? You said see it what?
70 y 7.
Oh, no, hear the second at all. All right, so 67. Okay, that one was too easy. As long as you find a prime number, the lowest prime number and the highest prime number, then you're good. I was expecting to hear 1, but I think I thought you guys before that one is the prime number. Anyway, all right.
Sir, what you asked for the lowest and highest prime number?
No, then that's what I thought. I asked for the infimum and the supremum.
Oh.
Just turn out the infimum and the supremum are the same lowest and highest
Yes,
prime numbers. Because the prime numbers would be 2, 5. Wait, sorry, leave out the 3. 2, 5, 2, 3, 5, 7, 11, right up to blah 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 blah. What the dots? Yeah, dot 67. And the smallest lower bound for the set, my mistake. The lowest upper bound for the set is 67, or least upper bound, and the greatest lower bound would be 2. So it just turned out that the greatest and smallest prime numbers were actually the infimum and supremum. So it was I wouldn't say coincidence, but it just turned out that it's highest and lowest.
And my Spanish was
Then
wrong. It should be 60, not
yeah,
70.
because theater is 70, right? What's it go?
70 is 70, yeah.
What? So what is theater?
No, Anthony, no, you.
7
Answer from
7 is
mash up your
7.
brain with
7
Spanish.
is 7.
It's
Right.
67.
Yeah, that's what I said. I
That's
correct myself.
yeah,
60.
correct. You said that. I don't know what you said the
60.
first time, but you was confused as ever.
I said
Whatever I
70.
said first was that right. That's all I do. All right.
70. But it's 60 is 70. 60 is 60.
Okay.
Yeah.
So T and S. All right.
This is being recorded. I don't want to get in trouble in the future.
Well, I'm teaching math, so if I get Spanish wrong, I say go. All right. Definition. Oh, by the way, you see these definitions, how important English is. If you don't understand what is being said, as I always tell students, if you have difficulty with English, you're going to have difficulty with math. Where were we now? Okay, next definition. But this one is just telling you, anyway, you will see what it's telling you. An ordered set S has the least upper bound property, if every non-empty subset E, that's a part of S. So if every non-empty subset E that is bounded above if every non-empty subset E that is bounded above has a least upper bound. And this is important for the real numbers. Let me show you an example now. That's going to knock your mind a little bit. Yeah.
Sir,
Mm-hmm.
and order set F as the least upper bound property if every non-empty, then you write the ECS as the least upper bound.
No. If every non-empty subset, you didn't write the word subset. If every non-empty
Every
subset
non-empty subset,
E,
yeah,
that, and you put the, you just put this symbol now to make sure you see that it's from S. If every non-empty subset E, subset of S, that is bounded above, has a least upper bound.
Alright, wait, sir. So that is bounded. That is bounded above. Above, sir?
Above, yeah.
Has
A least upper
the
bound.
least.
Has a least upper bound. You know what? Continue with it. That is.
Okay, sir.
Yeah, man, good. That is the supremum of E. So, supremum of E exists in S. Exists in S. That's what it's saying. So every subset E, every non-empty subset E, will have a supremum E that exists in S. In other words, that's like saying the same thing I just said a while ago. It has a least of a bound. All right. Look at this. I'm going to show you an example. So you can see something right here. Let's look at the set of rational numbers. Q, set of rational numbers. All right. So let's take a subset from it. And our subset will be X is in Q such that X squared is less than 2. So that's our subset. Remember, Q, we're using Q as our main set. So not real numbers now. I just want to show an example. So Q is our main set. And our subset, so in other words, Q is our S. And our E is this subset right here. Set of rational numbers such that the square of the rational number is less than 2. All right. What's the supremum of that subset? What is the supremum of this subset?
Sir, 2.
2.
Sir, 1.
All right, I hear 2, I hear 1. Write them down. I hear 1, I hear 2. I use Anthony. Nobody missing from this class. Michaela is here too. Come on, Anthony, Michaela, what you say?
So rational number.
Yes.
Rational number means can be written as a fraction.
That's right. Oh, they're deep in thought. Michaela fell asleep.
If you put 2 squared is not less than 2.
Wait. Answer the question you're giving me rational reasons for your question.
I'm trying to reason.
Me no want a reasoning, I want answer.
I'm trying to reason everybody's answer. It's between 1 and 2, sir.
All right. So I have to pick one.
As in the number lies between 1 and 2 is greater than 1 and less than 2.
Oh, and what is it? Michaela, are you here?
Sir,
Yeah.
it cannot be found then because if rational numbers are also fractions, sir, and
Yes.
when you find the product of the rational number, it has to be less than 2. And
Yes.
mathematically, you can get a number close. You can get a square of a number that is close to 2, but never reaching 2.
You're onto something right there, you know. So what you say, answer it.
Sir, but just no explain it, we never get no further.
No, man, you don't realize now you're saying the right things. So what is the conclusion based on what you just said?
How do I put it together now?
You put together already. The first thing you said was the correct thing, but I don't think you even remember what you said. Wait, Michaela,
Yes,
what is going
that
on, Michaela?
the fact that it is the when you
Oh, you're
find the
here, okay.
square of the x value, the square has the result has to be less than 2.
Mm-hmm.
No, I'm saying that the fact that rational number is also a fraction, so it's 1 point something.
Uh-huh.
You can find you cannot find a number that
All
will
right.
because each time you can go closer and closer as possible to 2 by finding the square of that fraction without
Therefore,
reaching 2. It's like infinitely close.
everything is so far is correct, but I want the conclusion based on what you just said. Anthony was onto something to you,
Okay,
but
sir.
he's not getting the conclusion.
I think it's like when you're doing limits.
How about this now, though, lad? Look here, man. Oh, you give a lot of reasons. Oh, anyway, all right. So you don't have an answer. Michaela, you have an answer?
Sorry, go ahead.
I was
Let
gonna.
me
I was. Well, she might just go. She might just come and say no, because she hasn't said anything.
It
Michaela,
doesn't exist. It doesn't exist.
what doesn't exist?
The supremum.
Why?
It's an
No, I
empty
want a
set.
reason. Okay, what's the reason for that now?
Because you get close but never reaching it. It's like
You don't
asymptote.
have to. You remember a while ago we had this set right here, 6, 14. We got close to 14 but never reached 14. But we realized that 14 was the supremum.
That is true. That is true.
So why are you saying there's none now?
Because with fractions, you will have infinitely many,
Hmm.
and you can't really get. So it be. Yeah, I can't figure how. I know if you're thinking about it's a number, probably 1.4 onwards. It probably lie between a range or something.
Okay, okay. So
That's
Sir,
my
Anthony,
thing.
but this is saying that
yeah,
x square is less than 2.
that's right.
It
So
didn't
your
say
each number in
x
that
square is
set,
less than
the square of it must be less
2.
than 2. Hmm? All right, look here. I don't want to mess up your brains today, man. Anthony's right, but I just wanted to make sure he knew why he was right. And that Jermaine, you were saying the right thing, but you wouldn't just conclude and say no supremum. That's what I wanted to say. It has no supremum, and here's the reason. So by the way, the person who said one, I don't remember who said one. Whoever said one can be the supremum because 1.1 is also in the set. 1.1 is less than 2. So 1 point, you need to get a number when the square of it is less than or equal to 2. Sorry, less than 2, beg pardon. No, root 2 would have been the supremum if Q was not the S. You see, if the real numbers was the main set, if real numbers was the main set and then E was the subset, then root 2 would have been the supremum because all the numbers would have been less than root 2. as Anthony was saying, 1.414, whatever it is. Now, let me make sure everybody understands this. You cannot find a rational number. It's impossible to find a rational number that is greater than or equal to all the numbers in that set. Sorry, I shouldn't say that. It's impossible to find the smallest rational number that is greater than or equal to every number in that subset. It's impossible. Remember, we're using rational numbers now, you know. So as Anthony said, that'll be fractions. So if you find one that you think is the smallest, I can find a smaller one than that. Because remember, when you're finding the least upper bound, you must find the smallest rational number that is less than all the numbers in that set. And you see, our problem now is that rational numbers, you know, would be fractions or decimals. So let's say when you find the square root of 1 point square root of, what's square root of 2? I think it's 1.414 something. I don't remember count to the 4. But let's say, for argument's sake, let's say it was this 1.4142678 just for argument's sake. I don't know what the answer is. I know it's start 1.414. Let's say when you put in the calculator, this is what you get, right? And somebody says, sir, the supremum would be 1.4142673 831. I can say no. I can find one smaller than that and say 301. Then somebody come and say, but sir, what about 001? If you get where I'm going, you can keep making it smaller and smaller and smaller. Previous one. So it's impossible to find a small rational number that is supremum for this set. That's why it doesn't exist. You guys understand that? I'm hoping. I didn't hear any questions, so that means you understand. Michaela, I need to hear your voice some more in the class, you know.
Yeah, but
even to say yes or no. Yeah. Go ahead.
if you have the square root of 2, anything added on to that figure there in the calculator would be greater than it?
Yes, remember that's why you want to find something that is greater than or equal to them.
Okay. But if you add on 0.01, wouldn't that be greater than the square root of 2?
Yes.
Okay.
But the square root of 2 is not in the setting, remember? Square root of 2 is not rational.
So,
Yes.
sir, you said greater than. So is it that we need a figure that is, because it said x squared less than 2. It didn't say x squared less than or equal to 2.
So what you're saying?
You were just saying a while ago that it has to be greater than or equal to.
To all the numbers in the set.
Yes.
Square root of 2 is not in the set, you know. It's not rational. Remember that our set, our original set was rational numbers. We know that square root of 2 is bigger than all the numbers in that set. Huh?
Yes, sir.
The square root of 2 is an irrational number. This is a member
yes,
of the i's. Or as some people might say, the irrational numbers written like this, Q naught. Same thing. Anyway, what was I saying a while ago? I don't remember. Oh, yes, root 2 could not be used. You see, if the set of numbers that E was taken from was real numbers, the supremum right away is just root 2. No number in that set will be bigger than root 2, and root 2 is bigger than every one of them. It would have been the smallest number that's bigger than all of those. So it would have been the supremum. But our original set was not real numbers, it was rational numbers. And root 2 is not a part of rational numbers, so it could not have been used. So if we remove root 2, it is impossible to find a number that is bigger than, sorry, I said that wrong. It is impossible to find the smallest number that is bigger than all the numbers in that set. Because as I was saying before, if some are, let's look at the board again. I want to make sure you understand what I was saying. Let us assume that what I have right here, circle on the board, is root 2. Of course, it has more numbers in it, but let us assume that that was the number. If you were going to say that, so remember, you want to find a number that is bigger than this, but smaller than all the other numbers that you can find. So if you were to say that, okay, the smallest rational number is 1 point all of that with a 1 at the end. 1.414267831. You say yes, add a 1 at the end. I could then say that I can find a smaller one than that by changing the 1 to a 0 and putting a 1 after that. That would have been smaller than the one before. You follow what I'm saying? Or you don't realize that this number is smaller than the one I had before. Well, I'll make sure I clear the board. Make sure you're clear on something. Use decimal places. Let's say this was root 2. Let's say that's root 2. If you want to find a number that's smaller than that, I mean that's greater than that, but is the smallest you can find, someone might say, okay, 1.4141 is the smallest number bigger than that, but that's not true. This number, 1.41401, is even smaller than that one a while ago. You realize that? That's what I was getting at. Do you realize that the third number is smaller than the second number? Use a letter. Do you see that A is smaller than B?
Yes, sir.
Okay. Then somebody could have come and said 1.414001. And keep going on with the zeros. So it's impossible to find the smallest number. That's what I was saying. If you take out the root 2, which we do because root 2 is not rational, then it's impossible to find the smallest number. That's bigger than all of those. And for read analysis, you need to be able to find supremums of the sets. That's why we could not use. That's why you don't hear about rational numbers analysis, because there are some criteria that needs to be met to have a proper analysis done on the set of. There's some properties that you need, and rational numbers does not meet that basic property. So we could not have used it for further
How did you
analysis.
come by root? Sorry. How did you come by root 2, by the way? Is it because you have x squared is less than 2?
Yeah, x squared is less than 2. So it means that x must be less than that was the original set? Yeah, x squared less than 2. Sorry. X squared less than 2. So if you use root 2, if you square root 2 right here, you get, well, not less than or equal, you get equal to 2. All right, let me just do it in mathematical way. Let me show you how I got it. Square root both sides. X squared less than square root of 2. So you get square root of x squared is just x, which is less than root 2.
Right. So the values you were choosing originally, you couldn't put something that would be greater, because you had what you had. I think you had
1.414, and I put on more numbers on it.
Yeah, you shouldn't put on any other number, because any other number would have been greater in terms of x.
If I made it smaller, then it would be there. Then you could find a number in the set that was bigger than it. So how do you go above? Remember, you want a number that's greater than or equal to all numbers in the set. If I went less than root 2, I'd be going less than the numbers in the set. And your supremum must be greater than or equal to all numbers in the set. So I couldn't go below it, I had to go above.
We wanted numbers that are less than or equal.
No, greater than or equal to all numbers in the subset. Remember, we're looking for supremum, you know.
Okay.
You follow me? You sure you understand?
Yeah.
Sometimes when you say okay a certain way, you know, sound like you understand, you know.
All right.
You sure you understand? Okay, look, hold on. Let me make it easy for you to understand. We know for a fact that root 2, right?
Yes.
Is greater than or equal to all numbers in the subset. You agree?
Right. And the subset was what again? That
was x squared less than 2.
X is a member of rational number.
And x squared less than 2.
And x must be less than root 2.
No, man. Well, all right, yeah, x must be less than root 2. Put it that way, good. So all the numbers in this subset.
So if you want a supremum, I don't see how you could actually go above that root 2, because you said it must be less than or equal to it.
Yes, but root 2 is not a rational number, so we couldn't have used it. So we had to go above it.
But
you follow me?
No, I can't follow you, because
right, follow me carefully.
Okay, let's say we use.
Yeah, go ahead.
Let's say we just use the decimal for root 2.
All right, let's say the decimal was 1.414. Just for argument's sake.
Yes. And we're saying a number must be less than 1.4, less than or equal to it.
But remember, every number in that subset, was less than or equal to that.
Right.
Every single number in there was less than or equal to that.
So
if you went
if you
below
put
it, you would be eliminating a number.
if you put 1.414, sorry,
Uh-huh.
1.414, and you put 0, 1, that cannot
Right.
be represented by x.
Can't be represented by x.
That cannot be represented as a maximum value for x because it says it must be less than that value.
Yes. Well, I think you're doing the same thing Lafferty did initially. You're thinking that the number has to be in the set. It doesn't have to be. It just must be a part of the original set, which was Q. You remember, your supremum does not have to be a part of the set. It just must be greater than or equal to all numbers in the set. Now, if you went below this 1.414 here, you would be going into the set, but probably eliminating some numbers. Because let's say, for example, you choose the number 1.41399999999 whole heap of 9. Because you want to go as close as possible to 1.414, right?
Mhm.
You would be eliminating a number in that set. Because every number bigger than this, but less than 1.414 is in the set.
So you have to go above it.
Yes, you have to go above to make sure you cover all of them.
That
However,
is kind of like cheating in a sense, but
kind of what?
I'm saying that is kind of almost like trying to cheat your way just to get all of them covered. But in
It's
reality,
not cheating. You have to make sure you cover them. You can't leave out any. Because it must be, the definition explicitly said it must be greater than or equal to all of them. So to ensure that that is covered, you have to make sure you go above them. Don't try to go. If you can't go below it, you're going to the
you
next
said
one.
less than, sir, not greater than.
No, man. All right. Before you go to supremum, your upper bound must be greater than or equal to all of them.
Okay.
Now the supremum must be the smallest upper bound. That's where less than comes in. I think it makes sense too. Your supremum must be less than or equal to all the upper bounds that you can find.
Okay. And your
But it
upper
must have
bound
a meaning.
itself must be equal to or greater than all of them.
Right. It must be equal or greater than all the members in the set.
So you go to the upper bound first in terms of the concept,
And then
and
you
then you
sort out
select
the
from
least
that
one.
in terms of the least one. Okay.
Correct. You don't start the other way around.
I got you.
Yeah. All right. How much time left? 7 minutes. Run to the next example quickly. Oh, definition. 7 minutes. Of course, you can write this. All right, people. Let's get to writing fast now.
So,
Next class,
sir,
I give you.
just a question,
Fine.
sir. You said that the supremum for E, that set that you showed us a while ago, would be empty.
Yes, there's no supremum because it
Okay.
was impossible to find a number that was greater than or equal to all the numbers there. The smallest number, sorry, that was greater than or equal to all of them. 1.5 is our upper bound because 1 bigger than all numbers in the set. 1.6, 1.452. But it was impossible to find the smallest one that's greater than or equal to all of them. That's why there's no supremum. Because the supremum was actually going to be an irrational number, which was not part of the rational number, so we're going to use it. Clear?
Sir, so could we
Yes.
have found the infimum
Could we have
from
found
that
the
same one that you
infimum?
had before?
No, it will be the same because this is negative root 2.
It's just like the supremum cannot be found.
Yeah, I can't be found.
Okay, that's the figure. All right, sir.
Okay, good question. All right, 6 minutes. Can I write down this in 6 minutes? Let's think about it. Set F, maybe not enough. All right, let's start it off. Oh, when you reach 12:20, we'll stop. So definition, we're going to define something very important. So make a note of it. That's what you define. So you can find it when you need it. We're defining the word field. What is a field? That's a very important requirement for everything I'll be doing later. What is a field? So this will just define all the algebraic properties that we need for our real numbers. Here we go. A set F is called a field. A set F is called a field. What is this? I said f is called a field if it has two operations defined on it. I said f is called a field if it has two operations defined on it, comma, addition x plus y, addition x plus y, and multiplication x times y.
Sir, my internet was down, so I was out for about when you started.
Oh,
You
we
see,
have to watch
the
your
last
recording because time is against us.
thing I heard is they're going to give us a definition.
What? Yep.
Sir,
Right fast, you know. Right fast, fast, fast. I said f is called a field. I said capital F. I should have mentioned that.
Yes,
I
sir.
said capital F is called a field if it has two operations on it, or two operations defined on it. Sorry. If it has two operations defined on it,
Okay, sir.
comma, addition x plus y. You write the word addition, you write x plus y. And multiplication, you write the word x times y, or xy. You have that?
Yes, sir.
Everybody know. And if it satisfies the following axioms. And if it satisfies the following axioms. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of them. First one, A1. Axiom 1, A1. If X is, I'm right on the board before I read it. If X is in F and Y is in F, so you should know what to write when I write on the board. If X is in F and Y is in F, then X plus Y is in F. So these are the axioms for field. You know. So if you have two numbers from the set and you add them together, it should still be part of the set. A2. I'm not going to read until we get to 20, then next class will finish. We'll continue. Axiom 2, or A2, sorry. Commutativity of addition. That's the name for it. Write the word, yeah. Commutativity, the fancy word, of addition. You know that word already. I mean, but you know what it is already. Commutative. You might forget what it is though. So let's go through it quickly. XY, right? The order doesn't matter. X plus Y is the same as Y plus X for all XY in F. X plus Y is equal to Y plus X for all XY in F. Right, everything we say now. X plus Y equals Y plus X. Write the word for and all XY in F. And this one is a symbol. This is a symbol for all. Write it properly. For all. Upside down V, upside down A, capital A. But anyway, write the words. A3. Everyone has A2? Good. A. Associativity of addition. You know how to spell that? Associativity of addition. Should have that by now. So here's what it says. The way the numbers are grouped, X plus Y plus Z will be the same as X plus Y plus Z. So the association does not affect the addition. For all X, Y, Z in F. 12:20 now. Okay, so I read one more and then that's it. No, stop here. So remember, next class starts from A4. So we have 1, 2, 3. So we have 8 more to go. And then let's discuss them afterwards. So these first 3 are straightforward. We know them already. And there are some. If you did modern algebra with me, you would that there are some additions that if you don't add it a specific way and add it a different way around, you get a different answer. So there are some special numbers that don't satisfy these criteria. So don't assume that every number satisfies this. Not every number does. They're called the quaternions. They don't satisfy this. Anyway, so next class we'll pick up from right here. This is next class is when? Monday? When did I say the first test? Because I'm really giving you questions to show you test it.
They didn't tell us, sir. Did you?
Okay, good. Thank God. No, I'm glad I didn't.
Great.
I told most of my classes that the first test is next week. So, but this class is ready for test. I have questions I could ask you, but you wouldn't know how to answer them because I haven't really shown the examples for all of them yet. So I want to make sure I show you some examples first. But I want to get through all of these so I can start some examples. Oh wait, I can give induction. But anyway, next class will start from here. All right?
So I remember we're supposed to get an assignment.